Okay, so this is a second topic on week number 2, the Broglie wavelengths. So the question is, can you calculate the Broglie wavelengths for the electron, right? So electron has a mass, and the mass is shown up in terms of kilograms here. Have a mass and has an energy of electron volts, and electron volts can be converted into a joule based on this. The one electron volt is corresponding to so many joules of here. So the Broglie wavelengths is the idea that any objects with a mass, let's say m, moving with a speed of a v. Okay, so let's say this is a small mass, such as electron, and moving at an average speed of a v. And then we talked about before, the kinetic energy, you remember, is on half of mv squared. Do you remember? And then momentum was an mv. So these are the quantities that from the Newton's law, you remember, classical mechanics. But now the Broglie wavelengths, lambda, so let me use a color here, the Broglie wavelengths, which is a lambda is essentially Planck constant divided by the momentum, mv. Okay, so the momentum is actually being used as a symbol called a p, and the Broglie wavelength m is essentially Planck constant divided by p. Most useful equation is Planck constant divided by m times v. And now let's just talk about the unit first. Planck constant is well known as 6.63 10 to the minus 34 joule times second, right? So that's the unit. And the mass here is a kilogram. Okay, and the velocity is meter per second. Okay, if you use them all, and this is in the unit of what we call the MKS units, which is a meter, kilogram, and second. If you choose to use the length scale as a meter, mass as a kilogram, and the time scale is a second, then naturally you have an energy unit of a joule, force unit as a Newton, and other units such as a pressure unit as a Pascal, and so on. So these are all the units when you use the fundamental unit as a length and the mass and the time over there. So this is essentially the length. So therefore, you should give the unit of a meter here. So that's a little bit of the details. When you plug in sometimes the numbers, here's now. Okay, so now let's look at this, the problem saying that, okay, I give you the electron with energy. Here is some kinetic energy they're trying to say, and they give you this energy in terms of joule. So from the kinetic energy, you should be able to calculate the momentum here. So there are many ways to do it. First way is from the kinetic energy, you can calculate the V, and then you can calculate the velocity, and you can use electron mass, and you can calculate, plug in all the numbers, you can calculate that. But one modified equation that you will find out is, let's say kinetic energy is on half mv squared, and what I want is, let's just multiply by mass of electron on both sides, and then therefore what you will see is mass velocity square which is this term, and will be a 2 times mass of electrons times the kinetic energy, right? So therefore, mv, which is a term, is 2 times mass times kinetic energy to the square root. Okay, so that would be my shortcut way, which is what I call the momentum P, and that's the one that I wanted to plug in right into here. So therefore, the shortcut way is, okay, so H was once again 6.63 10 to the minus 34, and the joules times second. Okay, so as long as I'm stick to the MKS unit, I'm okay here. And then here, let's do the square root and the 2, and then once again, this unit, right? This unit must be kilogram, right? This unit must be in a unit of the joule. So that's the rule that stick to the MKS unit, and you'll get this essentially answer, the lambda in terms of the unit of a meter. Okay, so what's my mass? And it's shown up here nicely as a kilogram, so that will be a 9.109 10 to the minus 31 kilogram. Okay, that's okay. And then what's my energy? And the energy was 506 electron volts. So this electron volt has to be converted into electron volts to the joule conversion. So that's the unit conversion that we learned in the previous chapters, sections, and then so that we can convert that into a joule. So what's this number corresponding? And the clue is right here. 1 electron volts is 1.602 10 to the minus 19 joule, right? 19 joules. 10 to the minus 19 joules. So therefore, okay, 506 and 1 electron volts and 1.602 10 to the minus 19 joule. Okay, so now you only carry the term energy in terms of a unit of a joule, and that's everything is shown up here. So now you are ready to plug everything into the numbers, and then you'll get this wavelength that is essentially 0.547 10 to the minus 10 meter. Okay, so that's the numbers, and then and what deBroglie wavelengths they ask, right? So the deBroglie wavelengths lambda they ask, and you probably want to change this into the nanometer unit, right? So nanometer unit is the final step is, okay, this is nanometer is 10 to the minus 9 meter. That means you have an extra term to be multiplied, 0.547 10 to the minus 1. So therefore, this becomes a nanometer, and this term becomes 0.0547. So that's why it's called a 0.0547 nanometer. You also chemists also use a term called angstrom, and angstrom is 10 to the minus 10 meter. Okay, so therefore this is also same as 0.547 angstroms. Okay, so these are all different length scale that we talked about as a chemist. So once again, so this is a question regarding the following statement. Say, okay, we have an electron has an energy, and that has a moving with a kinetic energy such as shown as an electron volts, and that energy can be converted into a unit of a joule. And then using the unit of mass kilogram, we can still use this deBroglie wavelength, which is also called as a matter wave. Anything that moves with a speed, okay, this can be described as a wave. So this is sort of the particle and the wave duality issues that was quite debated earlier in the century.